Yes, so welcome back, guys. So yeah, let's look at question 2. Yeah, so please, I want you to pay attention to this question. It's very, very important. Alright, so I'm going to read the question. I'm going to see it on your screen now. The effective capacitance for the circuit drawn below, or the circuit on the board, is, so we are basically asked to find the effective capacitance for this particular circuit. Now please take note of something very important. When you talk about a capacitor, a capacitor is not the same with a resistor. Alright, so yes, we have capacitors in series. Capacitors, okay, let me use the black so it can be more visible. So we have capacitors in series, and we have capacitors in parallel. Connection. Now I want to explain them quickly before we dive into this question. Are we getting it? Now, when you talk about capacitors in series, it's the same thing with resistors being in parallel. Okay, resistors in parallel is the same as capacitors in series, and capacitors in parallel is the same as what capacitors and as resistors in series. Now what do I mean? When a capacitor is represented by this, so please take note, these two things have equal, like they are equal. If they are not equal, then what you are writing is no more a what? Capacitor. Yes, this is not a capacitor, this is what? A cell. This is not a capacitor, this is what? A cell. But when they are equal, is what? A capacitor. Are we getting it? Now, capacitors in series. So let me quickly give an example. So we have a series connection of capacitors. Now please take note. Yeah, let me just do it like this. So let me say this is C1, C2, and C3. Now you have to find the total or equivalent capacitance. It's basically, normally in resistors we add them, but please take note, for capacitors in series, what we basically do is what? The 1 over C total is equal to what? 1 over C1 plus what? 1 over C2 plus what? 1 over C3. Do you understand? For capacitors in series. Now for resistors in parallel, let's say we have a resistor in parallel with, okay, let me draw it like this. Let me say we have a resistor in parallel, a capacitor in parallel connection. So something like this. So this is a parallel connection of capacitors. Now these two are equal, actually, not cell, they are equal. So we have C1 and C2. And I asked, find the equivalent capacitance. The equivalent capacitance C total we what? C1 plus C2. So please take note, for capacitors in parallel, you add them up, and for capacitors in series is like this. Now also note something very important. When two capacitors are in series, yes, we have a particular formula to represent them. Yeah, so two capacitors in series. So let me just clean this so you guys can see properly. So let's say we have two capacitors in series like this. Now what is going to be the effective capacitance? Normally when we have resistors in parallel connection, we say it's what? R1 R2 over R1 plus R2. Alright, yes, this same thing is going to apply to capacitors in series connection. Yes, so please take note, when two capacitors are connected in series, this is what is going to happen to the effective capacitance. CT is equal to C1 C2 over C1 plus C2. Yes, since this is basically jam questions we are treating, it's very important to understand this concept of capacitors in series connection. Now let's dive into the question. Guys, let's dive into the question. Now we have this kind of circuit. This is actually called a combined circuit, because we can see two capacitors in parallel connection. So this is one and this is one in parallel connection, and we have the parallel connection of these two capacitors in series to this guy. Yes, so the effective or equivalence capacitance is given as what? C total. So it's going to be the capacitance in series. We're going to add it with the capacitance in parallel connection. But please take note of something very important. Take note. This is basically the method of solving combined circuits. You take the series, you add with the parallel. But now, don't be confused. Look at this thing very carefully. 6 microfarad. Micro simply means 1 micro is 10 to negative 6. So farad is the unit of capacitance. So please take note of that. Now we have 6 microfarad here. Now what I'm going to do is I'm going to break this down to the equivalent form. 5 and 7, parallel or series, parallel connection. What did I say you do for parallel connection? Add them up. 5 plus 7, 12 microfarad. Now don't make the mistake of doing 6 plus 12. Oh, no, that's not what is written here. What is written here is basically telling us that when we have a combined circuit, we basically do it one by one and then sum them up. Sum the circuit up, not the value. Do you get it? We are going to sum the circuit, not the value. So I just basically sum the circuit. Now what is this producing? This is producing a series connection of 6 microfarad and 12 microfarad. Yes, so capacitors in series, I gave the formula. So what we basically say is what? C total, that's the equivalent capacitance, is equal to what? C1, C2, 6 times 12 over 6 plus 12. This is giving me what? Now, this is giving me 18, right? So 6 times 12 over 18. So this is jam. This is a jam question. You don't, I tell my students this, don't be quick to give the total answer. Yes. Now doing 6 times 12 will actually give you a problem. Yeah. But take note, when you now do 6 times 12 over 6 plus 12, 6 plus 12 is 18. We know that. Now what you now say is, okay, 6 here, 1, 6 here, 3. Do you get the gist? 12 over 3, 4 microfarad. 4 what? Microfarad. So please take note, 4 microfarad is legit for this question. That's the equivalent capacitance for this circuit. Yeah, let's move to question 3.